Hello everyone, I'm Yoongi. We chose a traffic flow for our project topic, so we are going to talk about a cellular automata traffic flow model. Research questions are about the origin, formation, and movement of traffic jams, and the effect of adding a lane. In our model, each cell has 7 states, and we use one-dimensional and two-dimensional cellular automata, and we use periodic boundary condition. Our assumptions for our model are simple. We assume a closed loop road, so there is no inflow or outflow of any car, and drivers want to move as fast as possible within the speed limit, and drivers reduce the speed to avoid an accident. And drivers reduce the speed with a certain probability, and this assumption is concerning human behavior. So drivers habitually decrease the speed with a certain probability, and we call this randomization probability. Also, in two lane, cars can change the lane. These are the car following rules. In the figure, the state of each cell is indicated with the speed of car when the car arrived at this cell. Look at each car, how they move. The first car at T0 is at the speed of 5, which is the maximum speed, and there's enough space ahead, so it moves 5 cells at T1. And the second car abruptly reduces its speed with randomization probability. The third and fourth cars reduce their speed to avoid the accident. In two lanes, lane change rule is added. So lane change only happens when gap between the current car and the car ahead is less than maximum speed, and there are enough gaps behind and ahead the car after switching the lane. Parameters we used in our simulations are on this page. We combined different values of parameters in our simulations. Cars are initially distributed randomly with speed 0. We simulated 500 time steps in each simulation. So total, we ran 180 simulations. These are the result of our simulations. So these are the time series diagrams for 1DCA. So we can see traffic patterns become more complicated with the increasing P, which is the randomization probability. Here, diagrams of 24 cars and 40 cars with the same P are compared side by side. In case of A, the initial linear traffic pattern remains the same all the time. And B and C, as P increases, the traffic pattern becomes more and more disorderly. All the jams are moving backward. It is the opposite direction of cars are traveling. And the figure A, it looks same as the Wolfram CA 184. And as you can see in the B, the lines that were shown in A start splitting and dissipated. And in C, the patterns in A are completely destroyed, but there seems to be some patterns. Empty cells are diverging, like trees are branching as they grow. We modified our model a little bit to allow any flow of cars. So starting from 18 cars, a car is added with probability of 0.3 at the first cell with speed 1, only when the cell is empty. So small jams appear from the beginning, and a thick jam begins to form at T is about 200. So when T is 500, there are 101 cars, and when T is 800, there are 133 cars. So we can see when there are only a few cars, the jam begins to form. So the traffic jam is the nature of traffic flow, and its emergence is unavoidable even when the vehicle density is very low. We drew 3 fundamental diagrams, flow rate to density, average speed to density, and flow rate to average speed diagrams. So Q is the flow rate, and it's the number of cars passing per cell per second. And we extracted the time average flow density and the average speed from our data. We observed the speed and the flow rates drop with increasing P. And if you see a simulation of 24 cars, it is obvious that jams get worse and worse as P increases. And in 40 cars, you can see the longest jam when P is 0.5. These are the time series diagrams for two-dimensional traffic CA. So overall features of the time series look very similar to one-lane traffic CA. Just one thing to notice here is that the cars look like going backwards, but it's just an optical illusion. They are not moving backward. They are moving forward. And other than that, they are very similar to one-lane diagrams. And these are fundamental diagrams for two-dimensional CA traffic model. Like time series diagrams, general shapes of fundamental diagrams are very similar to diagrams of one dimension. One dimension and two dimension fundamental diagrams are superimposed for comparison. We see that one dimension and two dimension diagrams are basically the same. Then dotted lines are for one dimension and solid lines are for two dimension. At low density, the one lane road generally performs better than the two lane roads, particularly at high P. And then if the number of cars does not increase, then adding a new lane definitely helps to relieve the traffic jam. But diagrams show that adding a lane does not improve the traffic flow if the density is the same. For our model, we found that the main causes of traffic congestions are the number of cars and the random fluctuations in drivers' behaviors. And the fundamental diagrams do not change much even when we added a new lane. Off-ramp and beltway may be partial solutions. It was very interesting project, and thank you for watching.